There's a really big upside to covering these two sections together. The first section introduces some important concepts using limits that derive some basic results that we'll need. But in the next section, we learn some new formulas that are easier to use than the basic definitions derived in the previous section. So to take advantage of the fact that we will discuss them both at once, I'm just going to summarize the important concepts from the first section and then jump straight into the second section, and that should really help streamline things and allow us to focus on the important formulas that we'll actually be using when we work the problems that you'll need to be able to work. So the big ideas, I guess there are really two big ideas from this first section, and that is a tangent line approximates the slope of a graph at a point. If you look at this graph here, this is f of x equal x squared, just a typical simple function. If you look at the point 1, 1, you can see that this tangent line that's drawn in touches at exactly one point, and you're sort of guessing, if you just draw it in by sight, where that line should lie. But if you assume that that's exactly what the tangent line does look like, it's fairly easy to find the slope. And what you'll notice, since you know that the slope is a change in y with a change in x, or rise over run, you can see that if you move from the point 1, 1, here you go 1 point to the left and 2 points up to get to another point on the tangent line. And that tells you immediately that the slope is going to be 2 over 1, which is 2. So in theory, you could take any function, make a good approximation of where the tangent line lies on a graph, and then approximate the slope by using rise over run. That's all well and good when an approximate answer is good enough, and when you've got time to sketch things out and that sort of thing. We're going to learn some ways to get around that, but for right now, the basic idea, the big idea, is that a tangent line approximates the slope of a graph at a point. So if you're at a certain point, the tangent line gives you a way of measuring how steep that slope is at that point. Second big idea is that the formula I'm about to show you allows us to compute the slope of the tangent line at any point on the curve without having to sketch it and approximate and just your best guess of where the tangent line lies. And that formula involves a limit. Now, because I'm just summarizing the big ideas, I'm not going through the derivation of that formula, but the punchline is, if you're given a point on the curve, the slope of the tangent line, which I'll call m, is given by this limit, if it exists. Now, that's the big idea. The details we can let go of for now, because we're not going to have to actually compute the slope that way. And that's the nice thing about covering these two topics at the same time, because now I will show you that there are some shortcut ways of finding the slope of the tangent line without having to either approximate or use some formula that's very hard to apply involving limits. The expression that gives you the slope of the tangent line has a name, and it's called the derivative. And this is the definition of the derivative, and if you'll notice, it's just the formula that I showed you earlier for the slope of the tangent line, but we're going to give it a name, derivative, and we're going to give it a symbology, and we're going to call it the function name with an accent symbol or a tick mark as a superscript of the function name, and you read that f prime of x. So the derivative at x is given by f prime of x, and it's equal to that limit. And that limit is the limit that gives us the slope of the tangent line of the curve. Now, as I mentioned earlier, if we had to do this using that formula, it would be quite a bit of algebra. Sometimes it would be almost impossible to do, and in simple cases, it would still be unwieldy. So it's good that we're not going to actually have to do it this way. You do need some terminology, though, because we'll be talking about derivatives for the rest of the semester. The process of finding derivatives has a name. It's called differentiation. And if a function has a derivative, we say that that function is differentiable. So you're building your vocabulary now. Derivative gives you the slope of the tangent line to a curve. The process of finding a derivative is called differentiation. And if a function has a derivative, it's said to be differentiable. We'll be using that terminology from now on. As I've mentioned, it can be very tedious and time-consuming to actually use this formula that I've got in the center of the screen here. And the good news is we won't have to. There are ways to do these derivatives without having to use this unwieldy formula. Before we tackle these derivative formulas, though, it might be a good time to mention that there are various common notations for derivative. The idea of differentiation, finding derivatives, slopes of tangent lines, all that was developed over a long period of time by various people in various countries, and the notation was never really consolidated. So you'll see various notations for derivative, and you'll get used to that, but do take note. We've already introduced the notation with the accent symbol, or sometimes I call that the tick mark. But there are others. If you write dy over dx, that means you're asking for the derivative of some function y with respect to the variable x. If you call the function y and you put the tick mark on it, you can say y prime. You can take the function name and put d over dx in front of it. That means derivative. And in some cases, you can just take the function name and put capital D subscripted with an x, and that means derivative. So if you see any of these things, you know that you're being asked to find a derivative. Now let's just jump right into it and learn these formulas that will give us a way of avoiding doing these things by definition, which requires a lot of algebra. Of all the derivative formulas that you'll learn this semester, the one that will be by far the most useful is this one. You need to practice this over and over again until you're absolutely an expert at it. It's called the power rule for derivatives, and it simply says if f of x is a function of the form ax to the n, then f prime of x, that is the derivative, is a times n raised to the power of n minus 1. Now this is very simple, but you need to make sure you understand what it's saying. It says if you start off with a function of the form ax to the n, to get the derivative, you don't have to use that formula. All you have to do is take the coefficient a and the exponent n and multiply them together. That becomes the new coefficient, the coefficient of the derivative. And then you have to go into the x to the power and drop it down by 1. Again, make sure you understand what you're going to do here. You're going to multiply the a and the n, the coefficient and the power. That becomes the coefficient of the derivative answer. And then you reduce the power from n to n minus 1. In other words, you drop it by 1. Very simple, but extremely important. Let's do an example or two. What if I give you the function f of x equals 2x to the third and ask you to find the derivative? If you try to use the definition, it would be a long algebraic calculation. With the formula, all you have to do is remember the process. You multiply the coefficient and the exponent together, and that becomes the coefficient of the derivative. And then you write down the base, which is the x, but you reduce the power by 1. So the 3 gets reduced down to a 2. And you should be able to do that in 10 seconds or less. It saves you so much work. Make the power rule your best friend because you're going to use it over and over and over again. Another useful result is that for expressions that contain multiple terms, the derivative can be taken by doing it term by term. And that's a nice thing to know. So for instance, if I have a bunch of things strung together with pluses and minuses, I can just do them term at a time, using the power rule or whatever rule it applies later to them. So I can take derivatives term by term. So if I want to take the derivative of that 3-term expression, I start off with the first term, which is 2x cubed, and I apply the power rule. The power rule says to take the 3 times the 2 and get 6, and then drop the 3 down to a 2. In other words, it's the problem we just worked above. But now you've got two more terms. So you've got a plus sign, then you move to the second term. The second term is 4x to the fifth. So what do? Apply the power rule again. 4 times 5 is 20, and you would drop the 5 by 1 and it becomes a 4. So the second term derivative is 20x to the fourth. Then you have a minus sign, and then you move to the third term. 3 times 2 is 6. Then you drop the 2 down to a 1, so you get minus 6x to the 1. And of course, you don't need the 1. An exponent 1 is understood, so if you want to write it as x to the 1, of course you can, but you don't really need the 1 there. And that's all there is to it. You should be happy to have a formula that saves you so much work. How about this one? If f of x is equal to 2x to the minus 1 plus 3x to the minus 3, then the derivative is, again, it's a two-term expression, so you can take the derivatives term by term. Start off with the 2x to the minus 1 and apply the power rule. The power rule says that you multiply the exponent times the coefficient, so that's minus 1 times 2, that gives you minus 2. And then you subtract 1 from the exponent. Well, if you take minus 1 and subtract another 1, you get minus 2. Then you've got a plus sign and you want to move to the second term. Well, the second term is 3x to the minus 3, so when you multiply the 3 times the minus 3, you actually get negative 9. So that plus changes to a minus. And you subtract 1 from minus 3, and minus 3 minus 1 is minus 4. Simple enough, but you do need to practice. Get rid of all your little trivial mistakes. Make sure you understand the power rule and how to apply it. Now, the ones we've done so far are the simplest possible examples of the power rule. You couldn't get much simpler than what we've done so far. But let's bump it up a little bit and look at some problems where maybe you have to either think or work a little bit harder. And maybe you have to rewrite something a little bit or something like that before you can actually apply the power rule. So we're going to bump the level up a little bit. An example of that would be if y is equal to 1 over x to the fifth, then what is y prime? Well, first thing you've got to realize is that 1 over x to the fifth needs to be rewritten so that it fits the power rule. The power rule has to do with something where you have x to a power. So you've got to think of that 1 over x to the fifth as a negative exponent. Remember that 1 over x to a power is just x to that negative power. So in this particular case, 1 over x to the fifth will be x to the minus 5. Now you can apply the power rule. And remember, if there's an understood 1 in front of that coefficient, so that's like 1 times x to the minus 5. So the power rule says you take the minus 5 times the 1, you get minus 5. And then you subtract 1 from the exponent. So minus 5 minus 1 is minus 6. Simple enough. How about this one? If y is equal to 2 over 3x to the fifth, then y prime is what? Again, you need to rewrite this so that it fits the form of the power rule. And I'll mention once again the importance of having gone back and watched the video that I did on algebra basics, preliminary stuff that's important to doing well in this course, and things like this problem is tackled there. You have to be able to look at that and rewrite it as a negative exponent. So what you need to do is think of that x to the fifth in the denominator as x to the minus 5 if you move it up. So the 2 stays where it is, the 3 stays where it is, the x to the fifth in the denominator moves up and becomes an x to the minus 5. Now technically you could put the minus 5 right beside the 2, but for our purposes it would be better to write it like this because now it looks just like the power rule. So applying the power rule, you take the minus 5 times the 2/3 and you get minus 10/3, and then you subtract 1 from the minus 5 and get minus 6. Here's another. If y is equal to 3 times the square root of x, then y prime is what? Again, that doesn't look like the power rule, but if you remember that a square root is a 1/2 power, then you can rewrite it and realize that the square root of x is x to the 1/2. And once you do that, you now see that the power rule applies. So you multiply the 1/2 times the 3. And then you subtract 1 from the exponent. Well, what is 1/2 minus 1? 1/2 minus 1 is 1/2 minus 2/2, which is negative 1/2. And this one, y is equal to 7 times the square root of x over 8. What is y prime? Again, that doesn't look like the power rule, but if you think of the square root of x as x to the 1/2, you can rewrite that as 7/8 x to the 1/2. And once you do that, you can see the power rule does apply. And you multiply 1/2 times 7/8 is 7/16, and then you subtract 1 from 1/2 and you get negative 1/2. Practice makes perfect, but if you don't get good at these basic ones that we're getting early in the course, if you're struggling with these and don't get that under control, can you imagine what kind of trouble you're going to be in later on when we bump up the level of difficulty? So do not hesitate to spend as much time on these basic ones as you need to be sure you're good at them and can do them rapidly and accurately, because once we bump up the level of difficulty, if you're still struggling back here, what chance do you have to get the ones that are at a higher difficulty level? So take this very seriously. Let's spend a little bit of time doing a few more of these with radicals. I'm going to just sort of do it this way, listing the original function, how you might have to rewrite it to take the derivative, then what is the derivative, and if necessary, simplifying it a little bit. So let's do a few of those. Let's start off with the function y is equal to the square root of x. Well, remember, that's just x to the 1/2, and the power rule says you multiply the coefficient, and again, you can think of that as being an understood 1 times 1/2, and then you reduce the power by 1, and so you end up with 1/2 times x to the minus 1/2. And that really doesn't need simplifying. WebAssign accepts that as a perfectly good answer. If you wanted to simplify it, get rid of the negative exponent, turn it back into a radical, WebAssign would also accept that, but WebAssign does not force you to simplify any further than that. Another example. 1 over the quantity 2 times the cube root of x squared. Well, again, you have to turn that into something that looks like the power rule. So I want to rewrite that cube root of x squared and think of that as x to the 2/3, but since it's in the denominator, when I move it up, it becomes x minus 2/3. This is the kind of manipulations you have to get used to and get good at. If you get stuck on these little algebraic manipulations, then how are you ever going to get the calculus part right? Because going from that step to that step is algebra. It has nothing to do with calculus. But now that we've got it in the form of the power rule, we can take the derivative by multiplying the exponent times the coefficient and then reducing the exponent by 1. So you're going to get minus 2/3 times 1/2, and then you're going to take 1 away from negative 2/3. Well, negative 2/3 minus 1 is the same as negative 2/3 minus 3/3, which is negative 5/3. And to simplify as much as you need to, all you've got to do is multiply the 1/2 times the negative 2/3, and you can see that the 2's cancel out. And you get negative 1/3 x to the minus 5/3. And again, WebAssign will accept that answer. You do not have to simplify it further. Another example. Y is equal to the square root of 2x. And remember, the 2 is under that radical as well, not just the x. So you have to treat those as a grouping. So that will be the same as the square root of 2 times the square root of x. The square root of 2 is just a number. So that's a number times the square root of x. And remember, the square root of x is x to the 1/2. Now it looks like a power rule problem. A number times x to a power. The power rule says you multiply the coefficient times the exponent, and then you reduce the power by 1. So if you take minus 1/2 and subtract 1, you get minus 1/2. And finally, just multiply. Remember, when you're multiplying fractions, it's top times top, bottom times bottom, and square root of 2 is like square root of 2 over 1. So you end up with square root of 2 over 2 times x to the minus 1/2. Before we continue, it might be a good time to look at a couple of special cases of the power rule where you can just call it a power rule problem, but it's such a special case that you almost want to think about it as its own thing. One special case is when the power of the power rule is just 1, when n just happens to be 1. Well, if n happens to be 1, that just means you've got x to the first power, which is just x. So an example of that might be something like, if f of x equals 3x, then what's the derivative? Well, if you actually apply the power rule you would think of that as 3x to the 1. So by the power rule, you'd take 1 times 3 and 3, and then you reduce the power by 1, and you get x to the 0. But remember, any non-zero number raised to 0 power is 1. So you really just get 3 times 1, which is 3. So when you look at it, you can see that if the function is 3x, the derivative is just 3. So in general, if you've got the derivative of a number times x, the derivative is just going to be the number. And if you think about it, that makes perfect sense because y equals 3x is just a straight line with slope 3, and the derivative is the slope of the tangent line. So in a lot of different ways, that makes perfect sense. Second special case is if the exponent is 0. If you have x to the 0, well, x to the 0 is just 1. So you just really have a number by itself. So you have 3 times 1 is just 3. So if you take the derivative of a number, what's that derivative? Well, again, if you want to really think of 1 as being x to the 0, you could think of that function as being 3 times x to the 0. And if you apply the power rule there, you'd multiply 0 times 3, which is 0. Subtract 1 from the exponent, get minus 1. But 0 times anything is 0. So the bottom line is, if you take the derivative of just a number, you're going to get 0. And again, that makes perfect sense in the context of what you know about a derivative. A derivative is giving you a slope of a tangent line. Y equals 3 is a horizontal line, and a horizontal line has slope 0. So the bottom line is the two special cases of the power rule, you can just look at it and see the answer. The derivative of number times x is just a number. The derivative of number is 0. Those are the two special cases of the power rule that you probably just want to sort out and think of in their own rights. So to summarize what we've done so far, you've got the power rule, and then you've got those two special cases. So this is a good thing to focus on to make sure you understand what we've done so far in this discussion. We basically come up with a power rule and then two special cases which might be thought of as rules in their own right. And remember that you can take derivatives term by term. So if you've got a bunch of terms strung together, you can do each derivative term by term. This is a very good thing to put into your notes, to put in one place so that you can go back and refer to it later very easily. Let's do some more examples. If f of x equals 1 over x squared, find the derivative. Well, by now you've probably got the drill down. You're going to write 1 over x squared using negative exponents. So that'll be x to the negative 2. Then you apply the power rule. The power rule says to take the coefficient, which in this case is an understood 1, and multiply it by the exponent, and then reduce the power by 1. Should be old hat by now. What if f of x equals 1 over the quantity 2 times the cube root of x? Well, again, we've done one similar to this. You know you're going to take that cube root of x and write it as x to the 1/3. And since it's in the denominator, it's going to come up as an x to the negative 1/3. So the cube root of x is x to the 1/3, but it's in the denominator. So when you push it up, it becomes x to the minus 1/3. Now it looks like the form of the power rule. Applying the power rule, you get 1/2 times minus 1/3, and then you reduce the exponent by 1. So if you take minus 1/3 and subtract 1, remember 1 is 3/3, so you get minus 4/3. Now about this one. You've got to make it look like the power rule, but this is a product. It's the product of 2x minus 1 times x plus 1. Now later on, we'll actually learn something called a product rule that will allow us to take derivatives of products, but right now we do not have such a thing. So the only way we could possibly handle this is to multiply everything out using the FOIL method and then simplify it term by term. So if you do first outer inner last and simplify the middle terms, remember the minus x from the 2x makes 1x. You get a simple expression that you know you can take derivatives term by term. So you start off looking at the derivative of 2x squared, which is 4x. The derivative of x is just 1. And the derivative of a number is always 0. So the derivative is 4x plus 1. Think about that. Make sure you're good with it. You multiply it out, simplify it, then take derivatives term by term. And notice that the power rule and the two special cases allow you to get 4x plus 1 as the answer. Well, this is actually a quotient. And we don't have a rule that tells us how to take the derivative of a quotient. We don't have it yet. So right now we have to do something different. And there's a trick here. I hesitate to call it a trick. It's just basic algebra. Whenever you have a multi-term expression in the numerator divided by one term, you can break it up into three different fractions. It's just the reverse of adding fractions with common denominators. You combine all the common denominators on one denominator and add or subtract the numerators. Here you're just going backwards. So whenever you see anything like that with a multi-term numerator and only one term in the denominator, the trick is just to break it back up into three individual fractions, and three in this case because there are three terms. So you can take the x and divide it into the 6x squared, you can take the x and divide it into the 9x, and you can take the x and divide it into the 5. And then simplify it. X goes into x squared and leaves x, so you've got 6x in the first term, going from here to here. And then when the x's cancel out in the second term, you just get minus 9, and then you just want to rewrite 5 over x as 5x to the minus 1. Now you have that in the form that you can take the derivative term by term using the power rule. So the derivative of 6x is going to be 6, the derivative of a number is 0, and then the power rule says you take minus 1 times 5 and get minus 5 and drop the exponent by 1 and get x to the minus 2. So if you leave out that 0, you get an answer of 6 minus 5x to the minus 2. How about this? Find the slopes of the graph of y equal x squared at various different values of x. Well, that's easy if you understand what the slope is. The slope of the graph means the slope of the tangent line to the graph, and the derivative is the slope of the tangent line. So all you got to do is take the power rule and use it on x squared, and you get a derivative of 2x. And then just plug in those various numbers. So you want to plug in a minus 2, and what do you get? Well, if you plug a minus 2 into the derivative, you get minus 2 in there, you get minus 4. Then you want to do the value at minus 1. Do the same thing. You take the derivative formula, plug minus 1 in for x, and that gives you a minus 2. Then you want to do 0, so you plug 0 into the formula, and you get 0. Plug 1 in, and you get 2. And you plug 2 in, and you get 4. So that's just a little bit of practice of applying what the derivative gives you. The derivative gives you the slope of the tangent line, and you were asked to find the slope of the tangent line at various points here. Find the slope of the tangent line to the graph of g of x equals minus 1/2 x to the fourth plus 3x cubed minus 2x at the point minus 1 comma minus 3/2. So here we're asked to find the slope of a tangent line to another graph. Again, the logic goes, the slope of the tangent line is found by doing the derivative. So the first thing we want to do is take the derivative of that g function. We'll let g is 3 terms, just do it term by term. So you take the power rule to the first term, and you multiply the exponent times the coefficient and reduce the power by 1, and you'll get minus 2x to the third. Then you move to the second term, use the power rule, and you'll get 9x squared. And then you move to the third term, and the derivative of 2x is just 2. And you have the derivative. But we want the derivative at a particular point. But remember, the value of the derivative is only determined by the x. So all you have to do is take minus 1 and plug it in for x, and that'll tell you the slope that the problem is asking for. So all we have to do now is plug minus 1 in to the formula we just derived from the derivative, and we'll find out, doing all the arithmetic, that the slope of the tangent line to the graph of g of x equals minus 1/2 x to the fourth plus 3x cubed minus 2x is 9. Practice makes perfect in all this. Basic ideas, derivative of the slope of the tangent line. The derivatives we're doing here can all be done by the power rule. And then you practice over and over again as you get really good at it. And that includes changing radicals to fractional exponents and changing negative exponents to positive or vice versa. All the little algebra related to doing those things, you need to practice it. Let's look at this one. Find the point at which the graph of the function y equal x squared plus 10x has a horizontal tangent line. I think the most urgent thing to pull out of this problem is what it means to have a horizontal tangent line. A horizontal tangent line is a horizontal line, and a horizontal line has a slope of 0. So probably the most important thing to pull out of that problem, at least initially, is the fact that they're asking you to find where the slope of the tangent line is 0. But the slope of the tangent line is given by the derivative, so we want to know when is the derivative equal to 0. So we take the derivative and set it equal to 0. So if you read that problem through, you have to pick out the fact that they're asking you for a 0 slope by phrasing it as a horizontal tangent line. Horizontal tangent line means 0 slope. So take the derivative, easily done by the power rule, 2x plus 10, and set it equal to 0. Solve for x and you'll find out that x is equal to minus 5. Now they asked for the point. Well, the point has an x coordinate and a y coordinate, so once you get the x coordinate, you still have to find the y coordinate. How do you do that? You plug the minus 5 back into the original function for y and find out what y is. So if you plug minus 5 in there, you're going to get, squaring the minus 5, you get 25. Minus 5 times 10 is minus 50. 25 minus 50 is negative 25. So the point we're looking for is the point minus 5 minus 25. So in going through all these, we've introduced the power rule, which is a big algebra saver in doing derivatives. We've reinforced the idea that the derivative gives you the slope of a tangent line. And we've also practiced rewriting things so that they fit the power rule. You've got to be good at all those things. Remember, this is just the very beginning of our work with derivatives. And if you're struggling with this, it's going to affect you the rest of the semester. So take whatever time is necessary to get these things to the point that they're just second nature. Doing the simplifications, doing the power rule, doing all these little things, they have to become second nature so you'll be able to tackle the more difficult stuff later.